Okay, we'll get started here talking about, basically what I want to do is just go over some basic definitions and units and things like that we're going to deal with all the time in thermodynamics. And so just a few things. A lot of the stuff you may have seen before, some of it you may not have, maybe in different ways, but there's definitely so important that we kind of go over this kind of stuff. So first thing is talking about mass and force. Okay, I know we've talked about this in statics and in other places, probably in physics. Hopefully you've talked about this as well. Mass, we've got two different kind of unit systems that we're going to have to work with a lot in this course. We're going to have to work with SI, or the metric system, and of course we're going to have to work with English system. Okay? And unfortunately, we have to just be able to go back and forth anytime. I mean, I could give you two problems in a row and you're in metric, and then boom, the third problem's in English. Okay? And you're doing the same thing, but all the data you're looking up is different because it's going to be in different units. Okay? And if you look at the back of your book, and you look at the table, the charts, and I sent you the charts, by the way, in your email. If you look at those charts, you'll notice that half of it is metric, and then the second half is English. So you're going to have to be going back and forth. And they give you the same chart in the metric system, and then later on, maybe 30 pages later, it's the same chart in the English system. So just got to get used to doing both. Mass in the metric system is the kilogram. So we are used to that one. So you all have heard that, I'm sure. And then we also have mass, though, in the English system. Now, in the English system, the standard, I would say, in most courses in the English system is the slug. Okay? That is the standard unit that we use for mass in the English system. But thermodynamics is a little different. We will not use the slug. By the way, a slug is a lot of mass. Okay? A slug is the mass that on Earth would weigh 32 pounds. Okay? It's like 32 pounds of mass. Okay? So that's a lot of mass. In fact, your mass is probably somewhere around 4 or 5 or 6 slugs, maybe 7, depends on your size. But, not a lot of slugs. Okay? So that is mass. Now that's going to be, you probably have seen slugs a little bit in other classes. You definitely will see it in dynamics in certain places. It's out there. But in thermodynamics, we use the term pound mass, called LBM, pound mass, a lot. Okay? Now, it's pretty easy to understand a pound mass, okay? Because if you have something, okay, some kind of box, and it has a weight of 1 pound. We all know what a pound is. We say, oh, I know what a pound is, of course. Pound's a pound. I know what it is. I can go to the deli and order a pound of turkey or something. Or I can go and get, buy it by the pound, all right? Or I go to Walmart and I've got my self-checkout and I weigh my broccoli, and it's a pound. Okay, whatever. So a pound is going to be the same thing as a pound mass. They're really going to be the same thing so long as we are on Earth. And considering that we're going to spend most of our time on Earth, I think it's a pretty good safe assumption, okay? So basically what we're saying here is a pound is a pound is a pound, okay? Whether you want to call it a pound force, okay, which is what traditionally a pound is. A pound is a force, not a mass. But we've come up with this thing called a pound mass. And it's basically the same thing as a pound force on Earth. It's the same amount. And so it's really the same thing. If you hand me something and you say, hey, this weighs a pound, it's a pound mass, okay? As long as we're not in space, okay? Now, if you said it weighed a pound force in space, then it's going to probably have a lot of mass. It's going to be much bigger, okay? But, in most normal applications, we can just go safe and go, oh, yeah, a pound force is pretty much going to be a pound mass. Okay? It's going to be basically the same thing. It just depends on the application. Am I looking for a force or mass? And remember that a mass, all that means is it's the amount of something. Okay? Force is different. Force is what it does under gravity. Okay? So you can have a certain amount of mass, but that doesn't mean you have the force, because you have to have gravity to have that force from that mass. Because remember that the weight of something is equal to its mass times gravity. Right? We know that. We learned that in physics. Right? And we recall that gravity, just as a little side note here, gravity is equal to 9.81 meters per second squared, or 32.2 feet per second squared. And those are two numbers you should have memorized, okay? You should memorize both those numbers. 9.81, 32.2. You should have those memorized, no doubt, okay? And the weight of an object is equal to mass, its mass times gravity. And if its mass is in kilograms, you use the 9.81. If its mass is in slugs, you would use the 32.2. Okay? So, yeah. But basically, in this case, what you're going to have is it's not going to be that complicated here. It's just going to be a pound mass. Okay? Okay? And that's going to be fairly easy to deal with here. Okay? So now, we've talked about mass. It's either going to be kilograms or pound mass. That's pretty clear. By the way, the conversion between the two, 1 kilogram is going to be approximately equal to 2.2 pound mass. Okay? That's another one that, it wouldn't be that hard for you to memorize that one either, right? And oh, by the way, speaking of unit conversions, they're all in the back of the book, okay? And on a test, quiz, whatever, you can always use the back of the book because you're going to need it for all your tables, okay? So if you ever need a conversion, that's fine, okay? And if somehow you're on your phone and you sneak off and you try to do a conversion, am I going to come down on you? No, not really, because I don't care. Okay? If you want to find a conversion on your phone, I don't care. I don't care about conversions because if you don't, I hope you memorize a few of these because it helps you. It just helps. Why I can't remember what G is in feet per second squared. Just remember that one. Use it so often. But, I'm not worried if you need to hunt a conversion. Whatever. Okay? It's not the point. All right. Force. Okay. So what are the units of force in metric? SI. Newtons, yes, a Newton, yes. Okay. Now, a Newton, abbreviated by an N, okay? All right, Newton. Okay? What we would say is that 9.81 newtons is the weight of 1 kilogram on Earth. All right? If you have 1 kilogram, it weighs 9.81 newtons. Okay? So there's your conversion. Pretty easy. You got 1 kilogram. Sometimes there's a unit of force called a kilogram force. Actually, Europe is starting to get into that more because in Europe, they like to say you have a weight of so many kilograms, but really you don't have a weight of kilograms. Kilograms is a mass, not a weight. Nobody has a weight of 20 kilograms or 50 kilograms or whatever. Nobody has that weight because it's a force. Kilograms is a mass and weight's a force. So some people in Europe are starting to say kilogram force. Okay? And that's basically like a pound mass to a pound force is a kilogram to a kilogram force, same idea. All right. Obviously, the unit of force in the English system is a pound force, which we'll try to denote this way just to make sure that you're clear that this is a pound force. I'll put LBF. Okay, try to be clear. Now, to help you a little bit with this, let me give you an analogy and a comparison. We've got 3 different units of force that I've just mentioned. 1 Newton is smaller than 1 pound force, which is smaller than 1 kilogram force. So let me show you the conversion. Well, obviously 1 pound force weighs 1 pound. 1 kilogram force weighs 2.2 pounds. How much is a Newton? A Newton is about 0.22 pounds. Okay? So it kind of gives you a perspective there between the 3 different forces. And again, a kilogram force is just the weight of 1 kilogram on Earth. Okay? So hopefully, most everybody's had physics, so hopefully you've done some of this stuff. It's not too crazy to go over this. I like this analogy too. I think this is really helpful. If you want a real approximation, your book has this, and I think it's a good analogy. If you want an approximation of how much is a Newton versus how much is a pound versus how much a kilogram weighs, think of apples. 1 apple is about the weight of a Newton. 1 apple weighs about a Newton. 4 apples weigh about a pound. 10 apples weigh about a kilogram. It's rough, but it works. So 1 apple is about a Newton. 4 apples to a pound. 10 apples to a kilogram. It's kind of a nice analogy. You can visualize an apple. Okay, 1 apple weighs about a Newton. If I had 4 in my hand, that'd be about a pound. If I held 10, that'd be about a kilogram. Yeah.
Should that be KGF or just KGF?
Oh, I meant KGF. Sorry, that's a good point. KGF. It is a term. KGF means kilogram force. Now, we're not going to use that term very often, but you realize when I say kilogram force, what I'm really doing is I'm saying it's the weight of a kilogram. Most people know kilograms, but they don't say kilogram force. All right, we spent plenty of time on weight and force, and hopefully that's a review. Okay. The only thing that's weird about thermo, again, is that we have the pound mass. We're going to use pound mass a lot, and nobody else really uses it except in thermodynamics. But, that's okay. All right.
American thermodynamics or all?
Well, I mean, other places, they kind of forced to use it some in other countries because there's so many things that still have that, relationships and things like that it's still used. But I'm sure it's used less, yeah. And even in our class, we'll probably use metric system 2-to-1 over English system. But, you need to be able to do both. So, yeah. It's still out there a lot, in a lot of different cases. All right, energy. Energy. Does anybody know what the unit of energy is in the metric system, the most basic? The joule, yeah, of course. So talking about energy, the most common one we're going to use is the joule, Joule. It will be abbreviated with a capital J, okay? And a joule is simply a Newton times a meter, Newton meter, okay? It's a force times a distance. Energy is force times distance, okay? So this is the simplest thing, is a joule of energy. Okay? Now, 1 joule of energy is actually a really, really small amount of energy. Okay? Very small amount of energy. In fact, the book does this, I think it's a good analogy, is if you light a match and let it burn, all that energy from 1 match is about a kilojoule, about 1,000 joules. So, yeah, 1 joule is not a whole lot of energy. That's a really tiny amount of energy. In fact, when we deal with energy, we're going to almost always be talking about kilo or mega, okay? Just to let you know, when we say kilo, like a kilojoule, 1 kilojoule is 1,000 joules, right? We'll be using that term. We'll also sometimes say 1 megajoule, and obviously that is 1,000,000 joules. That comes up quite a bit too. Both those. So that's a unit of energy. Does anybody know what the unit of energy is in the English system? Calories, that is actually one that is more in the metric system, but it is a good one. By the way, 1 calorie, okay, and we have to be careful with calories because there's calories like this, lowercase c, and then there's calories with an uppercase c. And there's actually 2 different things, okay? Not much different. 1 lowercase calorie is 4.1868 joules, okay? So 1 lowercase calorie, when I talk about lowercase calorie, this is the calorie that scientists and physicists and people like that have talked about for years. That's the kind of calorie. 1 calorie is about 4.187 or so joules. Okay. So obviously 1 calorie is not a lot of energy either. Now then there's a calorie that's the capital C. That's the calories we all know in food. Okay? Now what that means is it's 4.1868 kilojoules. Because 1 food calorie is actually 1,000 what you might call scientific calories. I don't know what the word you want to say. But it's 1,000 calories that we would use in physics, chemistry, science, engineering applications. Okay?
So why don't we have that calories and kilocalories?
Why do we? Because
why do we have the same word for...
I know, that's a good question. Why do we use the same word for 2 different things? That's a good question. I don't know the answer to why somebody would do that. But I can tell you why we do it with 1,000, because obviously, think about let's say you go to have lunch and say, hey, I'm going to have a 1 calorie snack. I mean, I don't know about what that's going to be, but that's going to be pretty tiny, right? A 1 calorie snack is going to be pretty tiny, and yet the energy in that is in the kilojoules. Yeah, maybe so. Yeah, maybe because we didn't want to say, oh man, I just went and had 200,000 calories today. Oh, yeah, I just ate 200,000 calories. Yeah, you can go and tell your friend or whatever, you just had a snack of 200,000 calories. And yeah, like what? Yeah, you're crazy. Yeah. So no, yeah. So, but yeah, that's capital C. That's the food calorie. Okay, that's the food calorie that we all know and love. So sometimes it's also abbreviated just CAL. Okay, so that's that one. Oh, by the way, the English unit for energy is actually something called a BTU. Okay, stands for British Thermal Unit. Okay? Yeah, BTU. Yeah. BTU is equal to, 1 BTU is 1.0551 kilojoules. Okay? Again, these are all just conversions. All just conversion. There's a conversion. There's a conversion. They're all just conversions. Okay? All right, one more thing. There is one more unit of energy that is fairly commonly discussed in the world, besides BTUs, joules. How many people talk about joules? Not too many. Now, if you go over to Europe, you might find some things that say low. They may put the energy in joules. I've seen that in packaging and things like that. But there's BTUs, calories, joules. There is one more unit of energy that is fairly common out there. Watts is power, but you're close. It has the word watt in it.
Kilowatts?
Kilowatts is more power. Kilowatt hours, yes. A kilowatt hour. Now, that leads me to the discussion about power, but there is such a thing as a 1 kilowatt hour. That's what you pay for on your electric bill, if you guys pay electric bills, and some of you do, some of you don't. 3,600 kilojoules is a kilowatt hour. Okay. So again, this is just conversions. If I say I have this amount of energy in joules, you should be able to convert it to kilowatt hours, calories, capital C calories, BTUs, whatever. It's not a big deal. Okay? Now, power, since we talked about kilowatt hours and started talking about power, power is simply equal to energy divided by time. That's all it is. Okay? Power is energy divided by time. It's the rate of energy. Okay? Now, the most common units of power are going to be when we have a joule per second of time, and that is a watt, which we will abbreviate as a capital W. A watt is a joule per second. So if you have 1 joule of energy flowing per second, that's a watt. Okay? And obviously, if we have 1,000 joules of energy per second, or 1 kilojoule per second, you have a kilowatt. Okay? If you run something that has a power of 1 kilowatt and you run it for an hour, you have consumed a kilowatt hour of power. Okay? And that's where you get the 3,600 kilojoules. Any other units of power? What? No, the energy. Other units of power. There's another one that's well known besides the watt. The watt is by far the most common, because even in the English system, we've gotten pretty much used to the watt and kilowatts and all that stuff. So. Yeah, I don't know. That's a long discussion. Why do we still use the English system? Metric is way easier, right? We should all be in metric, but that's a battle that's been fought for many years and it hasn't been won. So we still, as engineers, need to know both systems. Yeah, I know. It's kind of sad because think about all the extra time we spend just dealing with 2 unit systems. We could all just be in one. It'd be a lot easier. Horsepower. That's right. Horsepower. Yes. Horsepower is the other unit of power that's very common. Horsepower, HP, it is equal to 746 watts. Very good. Very good. Okay. So if we ask for something in horsepower, that's a very simple conversion. That's pretty much the most common units of power. I mean, I guess you could make up one, BTU per second or something like that, but usually if you're in the English system and they don't want you to convert to watts, they'll ask you for it in horsepower or something. And by the way, again, all these conversions are in the back of your book, so there's lots of conversions. Okay. Volts. Well, okay, yeah, voltage is not really a power, okay? Now, if you have a voltage times a current, that makes a power. V times I, then that makes a power. And if you use the standard units for volts and amps, you'll get watts. So you still get watts. Yeah. So. And by the way, we will at various times be working with electrical power. Not a lot, but we will use electrical energy in its application in some of the thermodynamics. So it's not something you can completely ignore. And we'll go over that in the context when we need to. Okay, temperature. Another one everybody can relate to, right? Everybody can relate to. Because we all know degrees Fahrenheit, and I'm suspecting that you all have heard of degrees Celsius as well. Okay? So that's easy. And you probably, if you haven't done the conversion, probably see it's not too hard. Degrees Fahrenheit is equal to the temperature, is equal to 1.8 times the temperature in Celsius plus 32. Okay? So that's a very simple conversion between temperature in Fahrenheit and Celsius, or Celsius and Fahrenheit. Again, you can Google it or whatever. It's easy. Okay? And both those temperature scales, I think, are not going to be that hard for you because you understand that. Okay? You understand, hopefully, 40 degrees Fahrenheit, that's fairly chilly out there. 40 degrees Celsius, that's pretty warm. Okay? And negative 40 degrees is the same in both of them. That's right. Yeah, because that's where the lines cross, essentially. Okay? Now, the hard part about this scale is it's what we would call a relative temperature scale. Okay? It's relative because, for instance, 0 degrees Celsius is the freezing point of water, right? And Fahrenheit has been set up with the boiling point and all this stuff. And so What it means is also is that it can go negative. Okay, it can go negative. You can have negative degrees Fahrenheit. You can have negative degrees Celsius. We all know that. Okay, they can both go negative. That becomes a problem for a lot of our calculations. And so what we need is an absolute temperature scale. Okay? Yeah, Kelvin. And I'm suspecting you've hopefully done a little bit of this in chemistry. Absolute temperature scale. What we mean by an absolute temperature scale simply is one that 0 means absolute 0. Okay, that's really what we mean. 0 means absolute 0. Can't get any colder than absolute 0. There's no such thing as negative Kelvin. You can't do it. Physically impossible. So, at least as far as we know. I hate to say things like that because then somebody proves you wrong. But as far as we know, we're pretty darn sure you can. So temperature in Kelvin, by the way, is equal to the temperature in degrees Celsius plus 273.15 degrees. 273.15. You don't really say degrees Kelvin, by the way. You just say Kelvin. It's very simple. If I ask you to take something that is in Celsius, and oh, by the way, there's a lot of thermodynamic applications that will say it's 27 degrees Celsius. If it's 27 degrees Celsius, there's a real good tip. You probably need to convert to Kelvin, because if you put 27 plus 273, you get 300 Kelvin. That happens a lot. Why? Because we want to simplify it for you, right? So yeah, we'll have a lot of applications that'll have 27 degrees Celsius, so that when you turn it in, it's 300 K. Okay. What is the absolute temperature scale in Fahrenheit, or not in the English system, relative to Fahrenheit? Anybody know what it's called?
You mean like the English version of Kelvin?
Yeah. There is an English version of Kelvin. Rankine. Rankine, yes. Rankine. Okay? It is the absolute temperature scale in the English system. It's the one that most people haven't heard of. You know, almost everybody's heard of Fahrenheit and Celsius, and if you've taken any kind of chemistry, physics course, you've probably heard of Kelvin, but very few people, until they get to thermodynamics, have heard of Rankine. The temperature in Rankine is equal to the temperature in Fahrenheit plus 459.67. Again, very simple conversion. Sometimes we'll say something is 40 degrees Fahrenheit, and you look at it and go, it's roughly 500 Rankine. 40 degrees Fahrenheit, roughly 500 Rankine. Okay? Now, one of the confusions that comes in thermo is that students have is they'll say, okay, this is all well and good, I get it. There's Kelvin, there's Rankine, I just learned this. And I know that I can take the same temperature, and I can have it either in Celsius or Kelvin, I can have it either Fahrenheit or Rankine, or even I can even convert between the two systems. Sure, whatever. I can do all that. But the question I'm going to get from students, and you're going to probably have this question yourself, so I'm going to just try to at least give you some help, is when would I use this absolute temperature scale? Why would I need it? Because sometimes I could get away with it. What's that? Gases. That's exactly kind of what I was thinking, and I'm going to try to make the bigger point of that. One of the examples is this. Why would we use it? Okay, now, what is that? Ideal gas? Now, it's a little different than what you might have seen. Maybe in your chemistry course they said PV equals nRT, or maybe they said P equals MRT or nRT. There's different ways of doing it. In thermodynamics, we usually write it like that. You might be like, well, why would we write any different? Well, usually because that V there is a little different. That V is specific volume, which I'll talk about in a moment. But regardless of this, focus in on this equation with me just for a moment. This is a very important equation. I hope you've seen it before in chemistry. It's not that hard. Okay, yeah, or a variation of it, same thing. Okay, So take a look at this equation. Let's say, for example, you wanted to solve for something, okay? And let's say you wanted to solve for the pressure given the other stuff. If that temperature is negative, does that mean you have a negative pressure? If that temperature is 0, does that mean you have 0 pressure? It doesn't make any sense, okay? So here's the takeaway. Here's what I'm trying to show you here. Here's the takeaway. Any time you divide or multiply, and a lot of our formulas divide and multiply by temperature, it must be an absolute temperature. You can't multiply by degrees Celsius. You can't multiply by degrees Fahrenheit. It doesn't work that way. You have to have it on an absolute scale. It has to be what we call a thermodynamic temperature scale. We'll get into that more later. Okay? So that's the principle. You can't multiply or divide by temperature. Let's say you divide by temperature and it's 0. I mean, that doesn't make any sense. You can't divide by 0. Okay. All right. Now, speaking of PV equals RT, the first letter in that thing, P, is for pressure, right? So let's talk about pressure for a second. P is for pressure. Okay? The most basic unit of pressure is what we call the Pascal. And usually we're going to abbreviate it with a capital P lowercase a. And by the way, 1 Pascal is 1 Newton per meter squared. Because pressure is really just a force divided by an area.
I'm guessing we're usually working in kilopascals.
Yeah, because 1 Pascal is not a lot of pressure. In fact, remember what I said on how much a Newton weighs? A Newton is basically the weight of an apple. 1 meter squared, I mean, that's like, a meter is roughly 3 feet. It's a little longer. Think about imagine a quilt. Imagine a quilt that was 3 feet by 3 feet. It'd be a decent sized quilt, right? I mean, it wouldn't be huge, but 3 feet. And then imagine an apple that was evenly spread across the entire quilt. You have to grind it up. I don't know, but just imagine. That's not going to be a lot of pressure, right? There's not a lot of pressure on that. Okay. So a Pascal of pressure is very low, very, very low. It's not really worth anything. Okay. It's so tiny. Okay. But what we're going to be dealing with mainly is kilopascals. In fact, the key thing you need to remember is atmospheric pressure. And again, here's another one of those things that you frankly ought to just memorize. Okay? It's not worth not memorizing. Atmospheric pressure is, at sea level, we define it as about 101.3 kPa. 100 kilopascals, so that's 100,000 pascals. 100,000 pascals. Now, I will say this. 100 kPa is a good approximation for any conditions near sea level, near and around sea level. Okay, what I mean by that is the pressure goes down as you go up in elevation, right? If you're in an application that's anywhere around here, or even northwest Arkansas, because here we're about 400 or 500 feet elevation. Even northwest Arkansas is like 1,400 feet or so, roughly. It's all about the same. If you go to the coast and it's 0 sea level, that's all. I mean, the pressure difference is very minor. Now, if we were to go to Colorado, and we were going to be in Denver, or we were going to go up in the hills, then that pressure is not a good estimate anymore. Okay? In fact, if you were to say it was 100 kPa in Denver, you could be up 10, 15% off. Okay? If you were to go way up in the hills, 10,000 feet, 15,000 feet, then you're definitely way off. Okay? And so, you know, it does vary quite a bit with elevation. Okay? The actual atmospheric pressure. But in most cases in this class, when we deal with atmospheric pressure, you can do 101.3 kPa, or you can just do straight up 100 kPa. You're fine. Okay? I'm never going to take off because you threw 100 kPa on there, you know, as an assumption. I'm going to assume 100 kPa is good. Because quite honestly, the pressure right here is probably right about 100 kPa. So, okay, by the way, what's the unit of pressure in English units? What do we use? Yeah, mercury is certainly one of them, but actually that's measured in millimeters mostly. And that's a different thing used in weather and things like that.
Pounds per square inches?
Yeah, PSI, pounds per square inch. PSI. That's pounds per inches squared. The thing you need to know about that is that atmospheric pressure is about 14.7 PSI. That's all you need to know. It's about 14.7. Okay. And if you want to convert between kPa and PSI, you got a conversion right there. Because 101.3 kPa is the same thing as 14.7 PSI. So there's your conversion. Or look in the back of your book, there's more conversions. Or Google it or whatever. I don't care. Okay? But mainly we're going to be dealing with kPa and PSI. That's really the two forms of pressure we're going to deal with. Okay? And by the way, one more thing about pressure that does happen sometimes. When you measure pressure, let's say in your tire, you're not really measuring absolute pressure. Most pressure measurement equipment you have, it's what we would call gauge pressure. Okay? Because the gauge pressure is equal to the absolute pressure, okay, minus the atmospheric pressure, okay? So in a very simple example, when you measure your tire pressure, and let's say you got an old school tire pressure thing, you know, you don't have the onboard one or whatever. You got an old school tire pressure monitor, tire pressure gauge, and you measure your tire pressure is 30 psi. The pressure inside that tire isn't really 30 psi. It's actually about 44.7 psi. Okay, the absolute pressure in the tire is going to be 14.7 psi higher than what you measure it. Okay, because what you're measuring is the difference between the outside pressure and the inside pressure. So to get the absolute pressure, you have to add in. You have to add in the atmosphere. So that's just a thing. Just something to remember. Because there will be occasional problems you'll discover that'll have the gauge pressure. Okay? Not the... Okay. You guys are getting tired. I get it. We're going to take a stop for just a quick moment. We've got to get this done. And then we're going to put you in groups and solve something real quick. And hopefully you're going to get some bonus points. Then we're going to come back. All right. One more thing here. This is easy. Density. Density is usually given by the Greek letter rho, okay? And density is basically the amount of mass per volume, kilograms per meters cubed, or it's pound mass per foot cubed. And again, it's mass per volume. How much mass is there per volume of it? Okay? And it's going to be either in kilograms per meter cubed or pound mass per foot cubed. I don't know too many others besides that we're going to use. And again, this is an area where us in thermodynamics likes to be different, you know. But in most of the world seems to use density a lot in other applications. I'm sure you've heard the term density. But in thermodynamics, we like to flip it. Okay? What we like to do is we come up with this thing called specific volume. And specific volume is simply the reciprocal of density. We usually do it as a lowercase v, okay, something like that, or whatever, lowercase v. And so obviously the units are going to be meters cubed per kilogram or feet cubed per pound mass. It's just the reciprocal. It's volume per unit mass. Okay? We're going to use specific volume a ton in this class. Tons and tons. It'll be very, very frequently used. Okay? Last but not least, this is important for what we're going to do with our little group exercise. There is a relationship between pressure and density. Okay? There's a very important relationship between pressure and density, or specific volume, but I'm going to express this in density. The change in pressure is equal to the density times the gravity, acceleration of gravity, times h, the difference in height. Okay? You're going to get to practice with that equation here in just a moment. The change in pressure is equal to the density times gravity times height. Now the density, I just gave it to you. Gravity, g, right? I said to memorize this. It's either 9.81 meters per second squared or 32.2 feet per second squared. And then h would be just the height difference. So if you were to, let's say you all know that if you go down into the pool, right, that it's going to be more pressure at the bottom of the pool than there is at the top of the pool, right? The change in pressure would be the difference in height between the top of the pool and the bottom of the pool, times g times the density of water. Okay? And by the way, the density of water, another one that you should memorize, is 1,000 kilograms per meters cubed. Don't ask me what it is in terms of pound mass per feet cubed, because I don't remember that one. Look it up. But I know it's 1,000 kilograms per meters cubed. Isn't that nice? Nice and easy. Density H2O. Not all densities, just the density of water. Okay. Now what I'm going to do is, let's do this here.